max-min test for quadratic function, and we use that idea to finally go to a second derivative test. So there is no calculus here, it's just basic algebra problem. Okay? If you have quadratic function, exactly quadratic function, right? Not quadratic approximation. The function itself is quadratic. And they're determining if you compute these numbers, and you can say if it is a maximum minimum or hyperbolic case or stuff like that. Right? So there are three coefficients in this quadratic function. If you calculate this one, this is a positive. If the coefficient a is a positive, you conclude is a minimum. It's not only local minimum, it is an absolute minimum. If you look at the entire xy plane, turns out g of xy in that case has a minimum value. Do you know what that minimum value is for this one? Turns out it's 0. The minimum value is exactly 0. You can't go anything below that. And if it's a maximum value, then it turns out that's the 0 case there, if it is a maximum value. If a is negative, you conclude that it has a maximum, global maximum, not just local maximum, for that quadratic function. And those minimum and maximum is actually 0. Okay? So do you recognize this term? AC minus b squared? This is called related, very closely related to which quantity? This is a D word. Close. Even more elementary algebra. Quadratic, right? You see this formula there, right? What is it called? It's inside the quadratic formula there, right? It's called the discriminant of a quadratic function. Discriminant, all right? All right. So p squared minus 4 that's a discriminant. That's the word. All right. So what is the idea here? A x squared plus 2bxy. How do you show it's the maximum minimum? That's all we have to do. That's the expression, right? How do you complete the square? How do you do that? If I call z in there, this is a method I usually use. I'll just do it easy way. So I usually pull out a and x squared plus 2b, and you have to put a in there and separate it like this. Fair enough? That is actually equal, identically. You can do that only if, under what condition? A is not 0, right? So you come back and think about, what if a is 0? What is the conclusion there? And things like that. But if a is not 0, then we can complete the square of that part. How do you do that? I hope in this class it makes sense by inserting the half of the square there, which is 4b squared divided by a squared, and minus 4b squared divided by a squared, and keeping the other term. Then these three terms makes a perfect square. That's the idea. Okay? So if you just group this one and send this one outside, then you have perfect square line up like this. We lose b2 there, and y and x squared. These three terms makes this perfect square. And I'm multiplying a to the outside, so I have 4b squared divided by just a, that's right. And here's plus cy squared out there, correct? And I missed that y squared there. There's y squared, because it has y in there. So if you multiply that, you do have y squared surviving there as well. And this is supposed to be negative, right? Does that make sense? So that three terms become perfect square. If you multiply a there, that a and negative y squared, and this out there. So this one, you have to turn that into common denominator. So if you put a in there, that's ac y squared, right? So all that gives you a times x plus b over a y squared plus all common denominator like this, a. Then what do you see? minus 4b squared plus AC, right? Y squared. Something's missing. But they have 2 in there. So this is correct. Oh, this is what I did wrong. This is supposed to be just b squared. So for example, if you expand b minus ay squared, you get x squared plus 2 times b a y xy. You multiply these two, and square of that part is b squared, a squared, and y squared. So you don't have 2b in there, just a b. You have to divide this one by 2 and then throw in there. So this correct quadratic part is this one without 4. So that changes this one to just that. So I verified it here. If you square that, you get this 3 terms. You have to subtract off so that it stays equal, and this first part become perfect square, and remaining part do not have 4 anymore. So that's AC minus b squared you see there. All right, so write that out in a better form. AC minus b squared. So what they're saying is that, for example, if A is a positive, so that one is positive, the denominator, that's positive, right? And they're saying AC minus b squared remains positive, right? So that's positive there. Then all the coefficient of this square plus and this square plus, they're remaining positive square plus positive square, right? What can you say about this quantity? It's always greater than or equal to 0. We did not use critical point anything. It's a basic completing square algebra that tells you this cannot go below 0. End of the question, right? This is always greater than or equal to 0. But can that actually reach 0? For which x value and y value does that actually reach 0? Yeah, x equals 0, y equals 0 does actually reach 0. So that completely proves that 0 is the only value there. Right, this only works for just for that quadratic expression. If you just cut this one all around it with the h-plane, you will always get concave up parabola. That's the conclusion. Make sense? So the other case is, what if A is negative? Yeah, this is negative and that's negative. That remains positive in that first item in there, right? This is always a positive. Only A is considered to be negative, keeping this one positive. So this one remains positive. So that whole thing's negative. This whole thing positive, negative remains negative. So it's negative, negative, right? Therefore, it's always negative number and also reaches 0. So you can conclude this is always less than or equal to 0. So therefore, it's a maximum case. And this A greater than 0, less than 0, and concluding minimum and maximum is analogous to second derivative test as well, right? If the second derivative value is positive, you have concave up, so you have negative, second derivative value negative, and that A part is analogous to that. But we have one more item in there called this discriminant, which is indeed determinant of 2 by 2 matrix that is associated with this quadratic form. So determinant was actually the correct answer too. If this is negative, think about it here. This is positive when A is a positive, and this is a positive, and that's negative, right? So we have opposite sign. Just like, for example, we can imagine the situation being like that with negative, some positive stuff in there, and a y squared. And that's, if we just look at one variable, another variable, that looks like a hyperbolic paraboloid, right? You know for that one, sometimes is a positive and sometimes negative. Therefore, it does not have a maximum minimum in there. So if that number remains negative, it keeps this coefficient of a first square and the second square opposite sign. That keeps this shape essentially hyperbolic paraboloid. Therefore, we conclude we do not have maximum minimum. Right? The logic makes sense? So, to conclude if it is a local maximum minimum point or saddle point, you just have to compute this discriminant, opposite sign discriminant, AC minus B squared, and this, the sign of A, then you conclude AC minus B squared negative, then you conclude it is not local maximum minimum. If AC minus B squared is 0, is inconclusive. You have to go to the cubic approximation and do a whole lot more horrible analysis to figure out what happens. But if it is not 0, we're lucky, there's this easy criteria. Make sense? For that quadratic. And next one is, at this point, we're going to accept that, all right, quadratic approximation is good enough. So if we have a function that is not exactly quadratic, and if you're looking at the critical point and believing that quadratic approximation is good enough, and you can use this idea to determine whether it's a maximum minimum. Okay? So that's, we're going to move on to that second derivative part. Let me relate the second derivative thing to what we just discussed in here. So this is called the second derivative test. This is what you actually use. And here's a critical point situation. We're looking at these 2 points. I'm going to just easily call A and B here for me to easier for me to write. Okay, and f of x, y, which is not equal to quadratic approximation, but is close to that, right? And what is the first term in quadratic approximation? No, f of ab. That's the constant part there. Then there's 1/2. Then fxx ab there, right? That's a number. This whole number is now serving as capital A, right? And there is x minus a squared. You can look at this as one variable like x1 plus fxy ab, and there's a product of x minus y and y minus b. I'm going to call that one x1 and y1 for you to easier for you to see. And here fyy, 1/2 is there, ab, and now this time is y1 squared since I called that one in there. Make sense? Yes. Critical point, that's right. Here's a critical point there. So f of ay, f of ab, plus 1/2. I'm going to call that one a in there. Well, I think this looks just fine here. This is a times x1 squared, right? Let me write a times x1 squared. Here is, if you multiply these two, a times b, no, it's just a b, that's equal 2 times b. You can always write this one as a 2 times b, and x1, y1, and c and y1 squared. So a is, what is a here? 1/2 of fxx value. B is 1/2, because this 2b must be equal to that, so b is fxy value, 1/2, and c is 1/2 of fyy value. So this being, with this mixture in there, how do we know after you do the little bit of transformation, linear transformation xy, how do we know it's a hyperbolic paraboloid or elliptic paraboloid is determined by the discriminant of this polynomial in there, right? So what is that discriminant here? AC minus b squared, that's what they said, right? So what is AC here? A is this one and that one, that one. So it's 1/4 of fxx, fyy, right? If you multiply A and C there. And what is B? 1/4 of fxy in there. So whether this remains positive or negative is really depending on this value, because they have common factor 1/4. Right? Squared, I forgot squared there. So if you are looking at one critical point, and if you want to know this quadratic part remains elliptic paraboloid or hyperbolic paraboloid, is determined by the sign of this quantity here, right? Sign of that quantity. So let me write it down again with a different color. It's all about this quantity, fxx, fyy minus fxy squared. If this is positive, elliptic paraboloid, right? So it's either maximum minimum. If this is negative, it's a hyperbolic paraboloid case, so it does not have maximum minimum. Okay? Rather than writing down ABC, I think this is more direct to me. So I wrote it like this. If it is a positive, and fxx being positive, what's the conclusion? Yeah, fxx positive and plus this one. Then we know it's local max and local min, but that one makes this whole thing local min, right? Yeah, local min. What about the other one? If xx is negative, that corresponds to local max, right? Under this condition, if this is negative, there's no local max. That's the second derivative test. When a equals 0, that which we didn't discuss before, right? This, if that thing is 0, one of the coefficient in here is a 0, or that one is 0, automatically hyperbolic. Right? So a equals 0, hyperbolic paraboloid. Or c equals 0. Right? If either this one is 0 or that one is 0, you can see this remains negative number if it is non-zero, right? So that kind of follows from this case as well. So if you have 5 critical points, then you want to only measure among those 5 critical points that correspond to local max and minimum to compute the highest point to lowest point. If there's a saddle point, you don't have to evaluate that. Remember, you actually have to compute the distance in that distance problem homework to figure out which one is a larger and which one is a smaller. You don't have to try this point because that's not going to be maximum, right? Saddle point. So you can toss them away. I don't know which one is easier, directly calculating the distance and determine which one is local maximum minimum, but it is still very good information, right, about the graph and what's going on. Advanced problem was, what if I have 3 variables floating around, x and y are all mixed up? How can you conclude it is local maximum min? You can actually complete the square again. So 3-term completing the square. So you have supposed to figure out completing the square with all 3 parts in there. Then you can conclude that's local maximum, local minimum. You evaluate these second derivative and compute this value a comma b. No need to simplify the second derivative. You usually end up at long and messy expression and second derivative, right? No need to simplify. Just plug in those number a, b, get the number out of it. But you probably need to simplify fx and fy, because if it is simpler, it's easier to take the derivative and handle it the better. So I recommend you to simplify fx and fy, but usually not necessarily for the second derivative, because all we want is a number, whether it's a positive or negative, right? Okay, so this thing makes sense? And it was a bit sloppy argument that quadratic approximation tells us this. From the quadratic approximation, this makes sense. All right, so I chose on any question? Number 3? Yeah, I'll have brief words on that one. But I'd like to do this practice. This is also homework problem 42 first. Then we'll get to that. All right? This is concept is simple. We're just practicing computing and organizing and all that. So it's a bit lengthy part. So let's begin with the first part. This is your exercise number 2. Just part 1. What do we do? What is the first thing we do if you have this thing like this? Find critical points. Find the critical points. Let's go ahead and find those first, and you write them down, and then we're going to do the test, right? And that part's straightforward, so we're going to focus on this part. I think it's a good idea if it is in the exponent of something or is in the denominator when you differentiate it, use this sort of simplified notation. It helps to organize information a little better. So, how about the first partial with respect to x partial in here? This part, okay? Agree? And especially if you factor out g when you differentiate one more time for the second derivative, that's usually better. I wouldn't factor out the common factor, and then it's a product of three things, and product will gets complicated. So this looks like a good form. Any question about fx and fy up to here? Make sense? So we set this one equal to 0, and e to the g will never equal to 0. That's a key thing in there, right? E to the something will never equal to 0. Even in a complex world, it never equals to 0. So if this is 0, this first factor is 0, and second factor is 0. And it is and, right? This must be 0, and this must be 0, correct? But when the first thing is 0, either this one is 0 or that one is 0, not both, right? Then it's guaranteed that the first equation is 0. Either first factor is 0 or the second factor is 0. So when x equals 0, then the first factor is 0. That's one possibility, so that these both are zeros. I'm keeping x equals 0. I take the second factor and equal to 0. That's the second possibility. Going back to the first equation, consider the second factor is 0, and the first factor is 0. That makes these two things 0. And second factor and the second factor here is 0. Those are the all possibility. This whole thing turns out to be 0. Full possibility. Make sense? And if you work it out, and then you agree that three things, first three condition gives you valid numbers, and last one is nonsense. This thing is sometimes 3 and sometimes 1. That never happens. So if you set this one 2 equals 0, that's not really giving us any critical points because of this AND condition. Should be AND. Okay. Make sense? So if you plug in these numbers and you get this 1, 2, 3, 4, 5 critical points. Fair enough? What? Yeah. And why don't we just, well, I realize that it's from here differentiating one more time. It is just similar calculation, and there's nothing like that. So I changed my mind. I'm not going to make the second one an exercise, but let's do this one together. All right? The second part is not an exercise, but let's calculate fxx, for example. It's here, correct? So we're differentiating this one more time. Then I'm differentiating this one first, so that's 2, and that's 6x squared, right? And that is 6y squared, correct? And it's e to the g. Then what do? Plus, and we're keeping all that as a product rule, minus 6xy squared, and e to the g multiplied by, right, g prime. G is here with respect to x, so that's negative 2x in here, right? Correct? So don't simplify. What we want is fxx of these values, right? At 0, 0, 0 plus minus 1, plus minus 1, 0, and you want to get those numbers. If it is a 0, 0, this is 0 and that's 0, right? What about g? If it is 0 and 0, e to the first, right? So that's 0, 0. So 2 times e. Is that correct? How about the other one in here? Whole thing is 0, so we can just write down a 0 here. So second derivative xx at 0, 0 is simply 2 times e, right? And then fxx, you can do this on your own, whatever that is. We need all this value to do the test at each of the 5 points, right? So after you calculate that, you will calculate those values, whatever that is. And then you calculate fxy, which is, same type of calculation. So, and compute all those 5 values, right? And then you go back, and with those all 5 values, and we for each of the case, we calculate what quantity? AB times fyy AB minus fxy squared. There minus fxy AB squared, right? Where there's a positive, negative, and you do the same criteria to get the local maximum, local minimum, or saddle point. From there you conclude neither local maximum minimum, right? Is there any question what to do after from here? I think that's straightforward. Fair enough? That was number 42. It's going to take us a long time to finish the entire thing. Yes.
Oh, what does the comma, why does the comma mean?
Here, very good. Here, to this condition is the first derivative must be 0 and the second derivative must be 0, right? So we're looking at each of the one sentence have two factors that make this one 0. But for the first factor, this one is 0 or that one is 0, not necessarily and. But any factor that is coming from the second one, when they're combining condition from the second line, condition from first line and second line, they must be and, conjunct by and, so that both of them being and. So I got this one from the first condition, this one from the second condition, so they must be and, so that both lines to be and. But this condition is nonsense. But all this thing here is and, right? This came from the first factor of the first condition and the second factor, first factor of the second line. There must be and. This x should be 0 and y must be 0. X should be 0 and this thing should be 0. But x is 0 there makes rest of the part plus minus 1. So all these commas are actually and. I should have put an and in there. Not clear enough to put in there, but all this comma here means and. But in between those are or, right? In between the bullet item is or. They cannot be happening at the same time. Either this is happening or that is happening, but individual condition, they must be all simultaneous and condition. Good question. Anything else?
Is that f or y supposed to be f of x on the 0, comma, plus or minus 1?
Right, you're right. This is supposed to be same fxx. Thank you. Then you compute this one and evaluate 5 points. Compute that and evaluate 5. Right. Thank you. Fair enough? So those were exercises. All right. Then here's a deal about the number 3. The argument, the way I explain this whole discriminant business is that f of xy is approximately equal to quadratic approximation. At the critical point, you begin with f of ab, and critical point makes this linear approximation part disappear, right? And then here's a quadratic part. If you believe whatever this means takes care of this business, and that's fine. If not, if you want to do require a little bit more rigorous approach to this, I don't know what you mean by this approximation and all that. What could be the better approach is what's in the number 3, right? Number 3 is basically this. Here's xy plane. Here's our critical points a comma b, and you draw an arbitrary line like this with this unit direction vector d, which is given by d1 and d2. And we talked about this plane h. Does everybody understand what this plane h is? Plane h is containing this L erected perpendicularly to xy plane. So here is that line. We call it a t line, right? Line L, but it's parameterized by t with the unit vector. So this will cut out the graph, which is a surface, with something like this for that direction d, right? But if you choose all the other directions, then this shape of the curve will change, correct? If I choose different direction d, how it cut out the surface, the graph of this 2 variable function, will be probably slightly different from that one. But what we hope is that whatever direction you choose, so here's a different direction, here's a different line t, maybe different shape like that. But for all 180 directions, if they all remain concave up like that, concave up all the time, then I think it's fair enough to conclude this is local minimum. This is a lot more rigorous than waving to this approximation and doing all that, right? This is a lot better argument. So what guarantees this concave up property is this function we call this ht, right? If you plug in this parameterization into two variable function, it becomes this one variable function in t. We practiced a couple of times. So what guarantees concave up? This function with second derivative at 0 is greater than 0. If this is positive, no matter which d1, d you choose, it remains positive all the time. That's concave up. From there, a lot more rigorously, we can conclude this is a local minimum. So in general, I took this chain rule and calculated second derivative right here without knowing what d1 and d2 are. So what is this second derivative here? H double prime of t, before we plug in t equals 0, is this guy here, using the chain rule a couple times. So the familiar shape showed up again, but it is not a quadratic approximation or anything. It is just evaluated in one line. Then you have this curve in the second derivative, and if this remains positive when you plug in 0, that guarantees concave up. What happens if you plug in t equals 0? These are constant, never changes. Only x and y changes to a and b as you plug in t equals 0. That's the point that they're a and b. So this turns to fxxab, fxyab, fyyab. And this d1 and d2 are freely changing. It can be anything you want, right? However, if the discriminant of this quadratic polynomial, such as this one, let me abbreviate it like this without a and b, if this guy remains positive, and if fxx is a positive, no matter what your d1 and d2 are, this whole thing will remain positive, right? As long as d1 and d2 are not 0, which is the case for unit vector, then this is always a positive. So that means h double prime of 0 remain always positive no matter which cut you make around the entire 180 degree. Therefore, it just remains positive. Every cut, you will have this concave up. From there, you can conclude it's local minimum. A lot better than this weird approximation idea, which we don't fully understand. Make sense? So, if you do, if it is like this, it is less than 0, is always less than 0, and so on. So this, concluding this is a positive or negative, there's no calculus. This is basic completing the square elementary algebra. From there, you can conclude that. Does that make sense? Yeah, this analysis helps us to go to a higher and higher derivative. I mean dimensions. All right? The details of this calculation is shared in that solution, but this is how much I wanted to mention today. Any question about the second derivative test? And it's a bit more rigorous approach to that? Yes? H of t? Right, h of t, good question. H of t is f of xy, where xy is not free, but is recomposed with d, involved the d. So there's a in there, and t times the direction d1, b plus t times the direction d2. That's the parametric equation of this line. So here, x is a plus d times d1, t times d1, y is b plus t times d2. That's a sigma t. So if you further compose it, it becomes like this, one variable function. How do you differentiate this one? What rule do we use? Multivariable chain rule. And that's what this one's here. If you do it one more time, multivariable chain rule, you arrive at this expression. This is more rigorous than using quadratic approximation idea. Formula? That's worth it. If we have f of xy, which is written like this, hope this makes sense. They usually have x and y in there, right? But we parameterize it what? Sigma t, which is a comma b plus t comma directional vector, which must be unit, and you don't go like that, right? So you further compose it in that. How do we differentiate this one if you don't even know what this f is? And let's say this one is ht, right? That's the situation. So how is h prime of t? Remember this? Multivariable chain rule. What is it? fx. Here, this is not a comma b. This is xy. Now, if you plug in t equals 0, then you know that t equals 0, that becomes a comma b. But before you plug in t equals 0, it remains as fx xy. Is that clear? And you multiply what? dx dt, which is? Here is your x, right? So what is dx dt? Alpha. That x part is very simple and specific in here, given like this. We don't know what fx is. What about the second term? fy xy. So if you further replace an x and y with this one, that would be that, but it's a lot easier notation to carry around here, right? So what is multiplied here? Beta, that is dy dt. So that's the first derivative, right? This tells you the tangent line along the section of the curve. Does this make sense? Along the section of a curve. The surface. Surface is like this. We cut it with this h-plane, and there's a section above it. Tangent line in that slope is computed like this. We used to be just interested in that, right? But we are now also interested in h double prime. Do you know why? Why are we interested in h double prime? Quadratic approximation. Why are we interested in quadratic approximation? Max min. To determine max min, derivative 0 is not enough, right? We want to make sure it's bend above and bend around there. That's why we're going in there, right? So let's do h double prime t. What is so fortunate about the h prime t? This guy being constant, right? No product rule. That's the fortunate part of this formula. So when you do one more time, you leave alpha there, you leave beta there. Constant multiple, no product rule, right? But when you do one more time, you do fxx, right? And let me just abbreviate it like this. Then alpha plus, right? And fxy beta, is that right? And this one, you're differentiating this one, fyy alpha, fyx beta. If you do it one more time. This is correct, right? Like this? fyx and fyy. Okay, thank you. Now, Clairaut's theorem, and then it's abbreviated, simplified it to, now I'm going to write it down, alpha squared, right? 2 copies of alpha beta, if it is continuous partial and all that, and we have fyy, x comma y, beta squared, correct? Yeah. Then if you want the derivative there, now this becomes a comma b, and this constant, nothing happens, and things like that. Make sense? Yeah. So in the homework, you're actually given